In this video, we're going to talk about some reactions of metals with either water or acidic solutions, right? What metals will react with water and acids, and how can we predict those processes? Okay, so some metals will react spontaneously with water. So if we look, water can be reduced directly. So if we look at the reduction of water by adding 2 electrons, we get hydrogen gas and 2 hydroxide ions. The standard reduction potential for that reaction of water is minus 0.83 volts. Now, let's go to a metal that we know reacts with water. If you've ever seen, sodium be put in water, right? Sodium sputters around, it will spontaneously catch fire. So sodium does react with just pure water. So if we look at the standard reduction reaction for sodium, right, we get a standard reduction potential of minus 2.71, right? They're both negative, but if we reverse the sodium reaction, we can make that positive, and we get a bigger positive than we have a negative for the water, and so we get an overall potential of plus 1.88 volts, right? That is spontaneous, right? So in general, any metal that has a standard reduction potential more negative than that of water, then that metal will react with water to create hydrogen gas. Okay, so we can just look on a table of standard reduction potentials. Any metal ion that has a standard reduction potential more negative than that of water, then the metal of that will react spontaneously with water to make hydrogen gas. Okay? So there's one set of reactions. Okay, some metals react spontaneously with acids, like hydrochloric acid in aqueous solution. And so if we look, right, here's our hydrogen ions, right? Hydrogen ions can be combined with 2 electrons to make hydrogen gas. That is the reaction we use as our standard, right? So it compared against itself has a difference of 0, right? So the standard potential for that reduction of hydrogen ions is 0. Nickel, right, is a metal. If it combines a metal ion, a nickel ion, if it combines with 2 electrons, you can make nickel metal. It has a potential of minus 0.23 volts. Well, here we've got 2 reductions. If we take the more negative one, flip it around, make it an oxidation, it becomes positive, right? This is still 0. You end up with an overall positive potential, right? So again, right, this is spontaneous. And if we're comparing the two, right, we take the one that is more negative, the reduction that has the more negative potential, convert it to an oxidation, and then that sum is positive and we get a spontaneous process. So again, right, any metal ion with a standard reduction potential less than 0 will react with acids like hydrochloric acid to produce hydrogen gas and the metal ion. Okay? So again, we can look at on our table of standard reduction potentials, and anything below the hydrogen ion in terms of standard reduction potentials, if we convert that into the metal, then that metal will react with acidic solutions to make hydrogen gas. Now, just to be clear, right, metals with positive standard reduction potentials, if we tried to reverse those, this would become negative. We would get a negative number here. So metals with positive standard reduction potentials, like copper, for instance, those will not react with acids. Okay? Some metals that won't react with either water or acids will react specifically with concentrated nitric acid. And it's because in nitric acid, the nitrate ion can act as the oxidizing agent, right? So the nitrate ion under acidic conditions can accept 3 electrons to become nitrogen monoxide gas, and then you get water left over in solution. And the standard reduction potential for that is plus 0.96 volts, right? That is a very favorable reaction under those conditions. So, right, something like copper that doesn't react with either water or hydrochloric acid, right, with its positive potential, if we reverse that and make, right, copper be oxidized as the nitrate is being reduced, right, we get a negative 0.34 volts, but that is more than offset by the plus 0.96 volts that we get back from the reduction of the nitrate to give us an overall potential of plus 0.62 volts, right? Making that spontaneous, right? Helps if you make an S. And so here we go, right? Again, right? Any, the standard reduction potential of the hydrogen ion was 0. So any metal with a positive standard reduction potential that won't react with something like hydrochloric acid will react as long as its standard reduction potential is less than the standard reduction potential of the nitrate ion. Because when we reverse that so that the metal is being oxidized, nitrate is being reduced, we get an overall positive potential, and so that makes that reaction positive. Now there are still a couple of metals, right? Primarily gold, right? So if we look at gold, right? Gold has a standard reduction potential of about 1.50 volts. So gold, right, has a standard reduction potential, and let me be clear here, right, that's positive, right? So gold has a standard reduction potential greater than the standard reduction potential of the nitrate ion. So gold is inert to even nitric acid. But we have still one more option if we want to react our metal to create a solution of those ions by an oxidation reduction reaction. So, right, we said gold wouldn't react with nitric acid, but gold will react with a solution called aqua regia, which is a mixture of nitric acid and hydrochloric acid. And it works like this, right? We said gold doesn't react with nitric acid, right, because the potential for that reaction is unfavorable. But remember, this is an equilibrium situation. So that doesn't mean we don't produce any gold ion. It just means that at equilibrium, the concentration of gold ion is really, really low. But if we add the hydrochloric acid, the chloride ions in solution complex with the little bit of gold ion that we make, and we know that these formation constants are really large. So this reaction is essentially a complete reaction that converts that small amount of gold ion into a gold tetrachloride complex ion. And that gold tetrachloride complex ion has a standard reduction potential that is lower than gold itself, which we said was 1.5. So if we create that gold complex ion and use that as our oxidation step, right, its potential is only 0.93. We reverse that, and so we end up with a potential that is small but positive, and so that is spontaneous. So if we have gold in the presence of chloride ions with nitric acid, it will react with the nitrate to produce that gold tetrachloride complex ion that is spontaneous. And so that is why aqua regia can dissolve gold, but other acids can't. So here is a table of standard reduction potentials borrowed from our book, right? And just as sort of landmarks, right, here is the standard reduction potential for water, right, minus 0.83, right? Here is hydrogen right in the middle at 0, right? And here is our nitrate nitric acid line, right? So we noted, right, metals like our alkali metals, right, lithium, potassium, sodium, right? They are down here, right? Lithium, potassium, sodium. Also, the more reactive alkaline earth metals, barium, calcium, and magnesium are all on that list. Those will react with water, right? This group vigorously, this group less so, in part because they are a little less reactive, and also because these tend to create oxides on their surface that protect them from water once they've had a little bit of reactivity, right? And so, right, there's that group, right? If we look then, right, metals like zinc, chromium, iron, right? Zinc, chromium, and iron have potentials between that of water and the hydrogen ion. So they will react with acidic solutions while they won't react in a neutral aqueous solution. Okay? So they're here in the middle. And then we've got metals here, right? Copper, along with things like, iron to iron 2, but copper primarily in this group, right? The reduction of iodine is in here, right? So things that will react with nitric acid like copper metal. And then, right, just to sort of remind ourselves, right, our gold is way up here, right? So gold standard reduction potential is too high to even react with nitric acid, but because we can use complex ion equilibrium to our advantage, we can get gold to be oxidized if we include a high concentration of chloride ions with the nitric acid to create the gold tetrachloride complex, which has a lower standard reduction potential than the gold ion itself. Right? So different ways that metals can interact with water, acidic solutions, nitric acid, and then the special case of gold with aqua regia.